Mic check. Okay. Good morning. I can see a few of you in chat. So good morning, Captain Price. Good morning, Glazer. Good morning, Tyler. Um, you're probably all sick of this class right now because you had the first project over the weekend. So I hope that at least for most of you, it would be great if it were all of you, but at least for most of you, you came away from that feeling somewhat successful. Either way, though, the first project's done and out of the way, and you can probably take a breather for a week or two before you have to, before you might start thinking about the second project. So I think for this week we can just focus on the small amount of new content, and then build on that in the coming weeks. So for now, in this class, the assembly class, we'll just settle into the regular routine for a while with no big spikes in the work effort, for at least a few weeks, I would think, for most of you. I will tell you that the second individual project is more difficult, because it is taking a semester's worth of work in the end. So at some point look at that, but I think you can afford to take a week or two without worrying about project in this class and just do the regular work. I'll probably at some point start giving you some hints or tips about how to go about. Is the mic off? Are people not hearing the mic? Oh, okay. That was Captain Price. Okay. So good morning. Good morning. I see it. See in there? Okay, so you were muted on your end. That's good. Sorry, I wasn't watching the chat for a second. I was just talking. So anyway, all I was really saying is you can take a breather for a week or two at least in this class in terms of the second project. So we only have two projects, but just so you know, the second one is more difficult. So at some point, I will start encouraging you to get working on it so that you don't find a huge massive work at the end, because the second one is bigger and more difficult. So Captain Price said it took him about 4 hours to do the first project, which is pretty good. That's pretty good because it's an unfamiliar language and it's kind of a one-off language that you're not likely to use again. Of course, it's very similar to a lot of high-level languages, but 4 hours is good. Okay, so here we are. We are in week 8. And we'll try to be enthusiastic about that because that almost puts us halfway there. Once you've sat through what I have to say this week, then we're roughly halfway there. We do not have a final exam in this class. We just have one last week of regular work in what is normally finals week. So the only reason I'm saying that we're kind of almost halfway there is because we have 17 weeks of content. So that last week, there's no final exam in this class. It's just one more week of a lab and homework. Just the normal routine. Okay, week 8. So we're talking about the stack. No, so Captain Price asked, does this HLA use goto? And it does not. It does have the assembly language equivalent, which is a whole series of what are called jump instructions on the Intel processor family. So pretty soon, at some point, well, I don't know how soon, but at some point we'll start talking about the jump instructions, and that's sort of the true assembly style goto. But HLA doesn't have a goto. What you want to do in high-level language is not use gotos anyway, but use the high-level constructs. So we use loops and if statements and procedure calls to get the flow of the code where we want it to be. So to get to different functions, you call them, you invoke them. Okay, so we're doing the stack, and I'll walk us through the content real quick, and then what I'm going to do is start with sort of the problem, and then talk a little bit about how the stack helps us to address a problem. So we'll talk about the stack, we'll come around to defining it in terms of how helps us solve a problem that I'll show you. But what we're talking about this week is the stack. If you've heard of a stack in computer science, it's a data structure. It's more or less built in to assembly language. So you always have access to it when you're doing Intel style assembly. And the way that you work with the stack is typically with push and pop instructions, which I've got my camera set up, so I'll draw a couple pictures. And then the homework is going to ask you to do the reading and look at a few of what are the potential limitations of the stack, which I'll also talk about some of those. And then we'll write a program that uses the stack to solve a particular kind of problem. Yeah, so poke and peek is probably similar, same idea. So less reading, I guess, than normal, and sort of constrained to a specific section of the text, a specific section of the text, the stack, and the push and pop instructions that we use in x86 assembly to manipulate the stack. The stack is a place where we store data. We put data in it and we remove data from it. Homework as usual. Lab as usual. I'm going to come back to this after I've walked through all the module. What's the discussion? Oh, I gave you is this class? Yeah, so I guess you're kind of getting 2 weeks of a little bit of less work in the class discussions. And remember, part of the point of doing the Piazza is just because it's at least for me anyway, it helps my frame of mind to know that I'm not alone in this. So we sort of have everyone there saying, hey, I'm out here, hey, I'm thinking about this stuff. And that's a lot of what Piazza is for. And then I also use it to get you to do some supplemental research sometimes as well. So this week's a little bit light. It's just let's say nice things to each other because we're halfway there. And then the reminder, so like I was saying, individual project 2 is the next big thing. It's not due until the last, the 16th, the end of the 16th week of the semester. So it's due the week before finals week. So that when we get to finals week, we'll just do regular content, but the project, you will have already put it to rest. So let me go take myself back to the lab. Okay, so I'm going to switch up my view and I'm going to go show you the problem first. So let's go look at a problem. And then we will look at how the stack helps us to solve this problem. Okay, so I will say this is stack.hla. As always, I'm being careful to make sure it goes in the folder where I'm doing all this kind of stuff. I'm usually careful, by the way, when I name programs. HLA has a lot of words that it is reserved for its own use, and it's very easy to run into one of HLA's reserved words. So I'm always kind of mindful of making my names be a little bit weird. So a couple of questions. So do we have a final exam? No, we do not have a final exam. Like I was saying at the beginning of the broadcast, the last week of the semester is a normal week for this class. We just do normal content. We have normal homework, normal lecture, normal lab. During the last week, no actual exam. The other question is, how do I prompt the user to press enter to continue? So I'll answer that in my example. Someone actually asked that over the weekend, and then they went and posted the answer in Piazza. So it's actually out there in Piazza, but I'll show you how to just do a sort of pause until they press enter kind of thing. But one of your classmates did ask about how do I get them to pause and press enter to continue, and then posted my answer to Piazza. Okay, so we're doing a program about the stack. I haven't talked about the stack yet because I'm going to show you first the problem, sort of in miniature. Yeah, that's probably true. If you're min-maxing the class, you can look at the points and sort of figure out where you should put your energies. Okay, so let's do the problem. So we'll start just by sort of challenging ourselves to not use any static variables. Now, one of the reasons why the lab this week has you do that is just to force the issue. But it's also good programming practice. When you write a procedure, so I'll just write a procedure that'll print the minimum of two values. So I'll just take a num1, which is an uns8, and a num2, which is an uns8. And then this procedure would simply do something like this. I'm going to do something wrong, so there's a chance to debug my code here. And I'm going to go ahead and type it out all the way. Well, it doesn't really matter. Okay, so let's just start with some basic review. So Captain Price got it. You cannot compare memory to memory like this, num1 to num2. So you have to offload. Doesn't matter which one. Make sure that you're picking a right size register, of course. So num1 is an uns8, so I'll use AL. And then I will say AL is less than num2. Although I will still use num1 for the output, and the reason I do that is so that I get decimal output as opposed to hexadecimal output. Now this is a sloppy procedure. We'll look at the actual lab in a second, but I'm sort of building up to making a point. Yeah, well, else can't be followed by anything, of course. So if you got caught out by compiler errors, no language that has if else allows Boolean expressions here. But the tricky part in HLA is that if you need a Boolean expression, then you have to mush else and if together. But for me, one thing to note here, by the way, is that I did less than or equal to, because technically that's the only thing that I know. If num1 is not less than num2, then the other thing that's possible is that num2 is less than or equal to num1. Now I could have written if, else if, but I'm really just looking for the minimum value. So technically if num1 isn't the minimum value, then they're both the minimum value because they're the same. But I'm doing this again to build up to a point. So there's a minimum procedure. Let's do a, just for fun, let's multiply them together. In fact, I'll divide them. I haven't gotten there yet, but I'm working up to making a point here. I'm going to purposely make myself have a problem. Okay, so I'll divide them. So I need to move, if we're dividing num1 by num2, then I will put num1, which is 8 bits, into AL. Then I will 0 extend AH to get myself a 16-bit numerator, basically. Then I'll fire off the divide by num2, AX. Remember, with 8 bits, AX represents now the remainder and the quotient. And then at the end I can say num1 equals, and then I will do type 1's AL, which is the quotient, comma, this is hard, it's a lot of stuff, and then type 1's 8AH, which is the, I need a space here. These are quite hard to do, the remainder. Now, I did this in part to review you on division, to make sure that you remember to do the 0 extending. So when you're doing unsigned 8-bit division, you divide out of AX, which you have loaded with the numerator value and 0 extended into AH. Yeah, it's not a bad idea, as Captain Price says, to write some notes for yourself about how this breakdown works. Especially since you're not likely to memorize this stuff in one semester's use, right? So it might be easier just to have some kind of page of notes or something that reminds you how to break these things apart. Okay, so why did I do all this? I did all of this so that I could, remember, we're trying to avoid using variables at all, so enter a number, 0 to 255. Get U8 goes into AL, and you can wish it to go somewhere else all you want to, but it's going in AL. You cannot change that. That's where the library puts it. Most of the HLA library procedures, if they return a value, they return it in one of the parts of the A register. You just have to know that. It's not going to change unless you go make your own HLA language for yourself. Okay, so we'll just start with what I hope you're already familiar with. Enter another number, 0 to 255. So this is related. Make sure you can actually see everything. Okay, you can. So what I have done here is I have created a problem for myself. Yes, there is a problem, and it's related to this stack thing eventually. And I'm going to use the stack to solve it. So what's the problem here? Okay, so I get an input in AL, and then I get another input in AL, which means that the original input is completely gone. So what we would normally do is we would set aside that value so that the next time AL gets overwritten, we know that we don't lose the original BL. And remember, we're kind of purposely trying to make ourselves avoid using variables so that we can have this experience with the stack. So I move AL aside, and then I get the second one. So I have the first input in BL as a consequence of this move. I have the second input in AL as a consequence of this second get U8. And then I can call procedures with them, so I can say min of BL, the first number, and AL, the second number. In fact, let's do a procedure to print them out. So we get the full glory of the thing, of the stack. Just print them out. Alright, so I made myself a little print procedure. I made myself a little minimum procedure. What's the smallest of the smaller of the two values? And then I made myself a little divide procedure that shows you the quotient and the remainder if you divide the first number by the second number. Okay, so down here at the bottom, after I get the two, I will print them, remembering that I am keeping track of the fact that BL has my first input, AL has my second input. Then I'm going to run the min, and then I'm going to print them again, and hopefully get my problem. So here we go. You can. So you can compare register to register, you just can't compare memory to memory. Okay, so notice what I'm doing here is I'm getting two inputs. I offload the one into BL so that the second input doesn't overwrite it. But then when I print it, I'm going to pass BL as the first number and AL as the second number. And then when I do the min, I'll pass BL as the first number, AL as the second number. And then I'm going to print them again. And then we should see the problem. Okay, so the numbers are 10 and 9, and then I discover that 9 is less than or equal to 10, and then something is wrong. So something happened that lost me my second input. It's gone. So what happened? Yeah, somewhere BL got overwritten. I should have done it the other way around, so I got lucky that it worked. But somewhere, values are getting overwritten by stuff. Somewhere BL got overwritten. Hopefully everyone saw that. I should have done this differently so that we could make it a little more obvious. But anyway, the point is when I went off to this minimum procedure, you're on the right track. So I printed 10 and 9, and then I did the minimum of the two values, and then when I came back to print, it said 10 and 10. So something about minimum broke my registers. And this could be a very difficult puzzle to solve, but fortunately there's an easy way to solve it. So the problem is, or at least the problem can arise when you create a procedure that overwrites a register. So notice here I am overwriting a register. And that can be a problem if your registers are your data. So my data is BL and AL, and because I have procedures like min and like divide that actually use move instructions to overwrite the data, that can break my data. You can make local variables, but remember we're trying to not use memory as much as possible, so we're going to use a different technique instead. So we're going to use what's called the stack. So the stack is a data structure and you get it totally for free, and I'm going to show you a usage of it, and then I'll go show you pictures of how it works. So one thing to remember here is that whenever you have a procedure that overwrites registers, you should be using the stack. That's what I want you to do. If you notice that you are overwriting the data in registers, you should use the stack because you don't want an overwrite of a register here to break your data somewhere else in the program. So how does that work? The A register is having its data altered by this procedure. And the only reason the procedure does it is just for this one little comparison. So I'm going to use the stack, and the way you do that is, and you always do it with 32 bits. You push the data onto the stack. Yeah, you're going to use registers a lot, so this will be a handy trick, especially if you're trying to reduce the amount of variables. You push EAX, and the effect of that, and I'm going to draw a picture of it in a second, is that you sort of make a copy of that data into the stack data structure that you always get for free on Intel. It's just there. So now I've made a copy of all 32 bits of the A register onto that stack, at which point I can go and I can ruin the A register in any way that I want to, because when I'm done at the end, I forget how to get out of that. Oh yeah. When I'm done at the end, I can use pop to retrieve that set aside data. So if you push data onto the stack, and then you go and you mess around with the data all you want to, like I'm moving num1 into AL here, if you pop it at the end, you restore the original data around whatever mess you made of it in your procedure. So since I'm overriding AL, I'm going to push it to the side. Then I'm going to override it, use it however that I need to, and then I'm going to pop it when I'm done. So now I'm going to draw a picture of that. So I'm going to turn that off. I want the document. All right, so sorry, you're going to get the camera stuff. And I know there's a little shadow here. It's the best I got. So the stack. This data structure is just always present when you're doing x86 assembly language programming. It's very, very useful that it is provided as a part of the work that you just do, you get automatically in x86. Anyway, it's always there, and it's a data structure that allows you to preserve data as your program's running so that you can restore the data later. So let's say, for example, that, well, what I just did, it doesn't really matter, but let's just say that I enter the values 10 and 9. So in my program, when I push EAX, I get all 32 bits, including the AL part, but effectively what pushing EAX does is it pushes that 9 onto this stack. So now I have a copy of this data, and now I can do things like move 0 into AL. So I can overwrite this AL because the stack is sitting there preserving a copy of it for me. So I move 0 into it, I can increment it if I want to, and I can sort of use AL however I want to temporarily, because the stack is preserving that data for me from the push. Now when I'm done, I pop EAX, and what happens is this 9 that I pushed onto EAX, it is restored. So the act of pushing a register on the stack copies that register's data on the stack. The act of popping the stack more or less removes, but copies that data back into wherever you pop it to. So push to preserve data, and then mess around with it, do math, do decisions, whatever you got to do with that register. When you're done, then you pop it to put it back where it started. So it's a really great way to write procedures in the HLA language or in x86 assembly. It's a really great way to write procedures that alter registers without breaking the whole rest of the program. Okay, so the question is, what if we want to stack the BL data? So let's do that and see what happens. So let's say we wanted to push them both on the stack. So we could push EAX, which would copy the 9 onto the stack, and then we could push EBX, which would copy the 10 onto the stack. And I'm glad you asked that question, Garsavak, because this is an important thing to understand about the stack. The reason why we call it a stack is because every time you push something onto it, they stack up from bottom to top. So let's say that I had a third input. And I push, so let's say I had a third value in CL, well, I could push ECX, and now I've preserved 15, 10, and 9 on the stack. Now the catch, the trick is that the stack only works in order. So you always push on top of what's already there, so the stack grows. When you pop, let's do it wrong first. And then we'll come back and we'll do it right. So let's do it wrong first. When you pop, let's say I pop EAX. When you pop, what actually happens is whatever is on top goes to where you're popping to. So if I pop EAX right now, I accidentally put the 15 back in AL. If I pop EBX second, I get lucky because the 10 comes back. And if I pop ECX third, then I get the 9. So because of the way stacks work, you push on the top and it stacks up, and then you pop from the top. That makes the stack go back down. It potentially can be confusing, at least until you've practiced it. So this is wrong. So I push ABC, but when I pop ABC, I actually end up accidentally mixing or switching two of the values when I restore them back to the wrong place. So that is wrong. What's the correct way to do it so that things go back where they came from? Put the stack back. So what would be the correct way to pop these so that the data goes back? That's correct, Glazer. Good one. So you have to pop in precisely the reverse order of the way that you pushed. So you have to pop ECX, which pops the piece of data from the top of the stack into, basically copies it to ECX. So that puts the 15 back where it belongs, and then we pop EBX, which puts the 10. That one always worked because we got lucky, and then the last is EAX, which takes that 9 and puts it back. So if you have to preserve multiple registers, then you need to be careful because the order that you push is the exact opposite of the way that you pop, and the reason that is because of the way stacks work. Now, why a stack then? Why a stack if you're kind of being set up to make this mistake? Computers can execute stacks very, very fast. This is about the fastest way that the processor can offer you this functionality, is with a stack. So the stack is super useful for preserving and restoring data. Push to preserve, pop to restore. But to maintain maximum performance, the stack only does from the top. So push to the top, pop from the top, which means that you as the programmer have to remember that you push and then you pop, but you pop in exactly the opposite order of the way that you pushed to put things back where they started. So that's the stack, the x86 stack structure. If we were doing ARM assembly, it also has a stack that works the same way, you push and pop. Although in ARM it's a little bit easier to program. in Intel. Now there is a convenience function, but we're not going to use it yet. That makes this a little easier because I want you to understand how the stack works. So the stack high performance data structure, only having to work from the top of the stack. The only thing that the processor actually has to do here is keep track of the top. So this thing can move up, it can move down. There's actually a special register for that called the stack pointer. So Intel actually has a special register that allows it to keep track of the top element of the stack constantly. And this moves up and down as you push and pop things. Pretty neat. But again, because it is made to be high performance as fast as possible, it means that you have the responsibility as an Intel assembly programmer to use it correctly. Push in one order, pop in the opposite order. I usually put the letters in order myself because it's easier to remember, but it doesn't actually matter as long as the pop is an exact mirror of the push, a reflection. Okay, so that's that stuff. That's the stack. So let's go back to my little example real quick. So that's why so the trick to using the stack is to look at your procedures and try to identify the registers that your procedure is altering just for the purposes of doing a calculation. So in the example of divide, it's altering a register for the purposes of doing a calculation. So I owe it a push here if I want my program to work perfectly well. So for divide, what should I push? Right here in divide. Hopefully you can see my screen. Okay, I did change. Do you know what register goes in there for divide? So AL technically, yes, EAX. So Gersebach though brings up a good point that I should make. Now technically notice the divide actually alters all of AX, and technically you can push AX, you cannot push AL by itself. So you can't push AH or AL by themselves. You can push AX by itself, but so you cannot push the 8-bit ones by themselves. You can push the 16-bit components by themselves, but your book and the Intel documentation will tell you that the processor actually handles it more efficiently if you push the whole 32-bit thing. So even though we only actually have to preserve AX, the processor will handle this faster if you push all of EAX. So even though you're only really touching, I mean, it looks like the smaller bits, you want to push the whole 32-bit register to get maximum performance. I owe it one other thing. So what's the partner of pushing to preserve the A register stuff, and then I do a calculation in it, and then I print the results of that calculation? What's the last thing that I owe it? Good one. Pop EAX. So that restores the A register to whatever it was. Okay, so that's sort of the reason why. Hopefully you saw that. The reason why print doesn't have a push or pop is because it's not altering registers. Now let's do a tricky one before we switch over to the lab. Yeah, I'm doing okay on time. So let's do a tricky one real quick. So this one's going to exercise the brain just a little bit. I'm going to replace this code. So I'm just going to turn that into a procedure and then call it. So get number. Okay, so sort of I'm telling you up front, but be brave and venture an answer. This get U8 we know is going to alter the data in AL, so this one's tricky. So we'll just start with do you think I should or should not do a push and pop because I know that the get U8 is going to alter the A register. So you can just say yes or no if you want to venture a guess. So does get number need a push and pop, knowing that underneath here HLA is actually about to alter the A register? So no is correct. We do not want to push and pop here. It's not quite perfectly accurate to say it's because it's the first procedure, even though that would work out. This one's hard. So no, we do not want to push and pop. The reason that we don't want to push and pop is because we actually do want the procedure altering the A register. So this one's the hard one. But when you've written a procedure where you want the register to be changed when the procedure's done, then don't push and pop it. So when I get out of this procedure, I want it to have changed to A. So when I call it, I want it to have changed to A, which means that I don't want it to push and pop A. I want to get new A out of it. So that can feel pretty subtle. That's a hard one. But if you have a procedure that's returning data in a register, then you don't want to push and pop that register because you actually want the register to be altered by the procedure. But if you have a procedure that's not supposed to return data, like our min procedure or our divide procedure, these are not supposed to return data, they just do work. That's the time to look for preserving data. But that get number one, that's hard. So hopefully I've steered you on the lab in the right ways. Okay, so the stack. It is a data structure that you can more or less just consider built in to Intel assembly language programming. Its purpose, the way we will use it, is to preserve information. We can reduce the number of variables we use if we store those variables in registers. But we have to be careful that we don't lose data because the registers are so volatile. The data in them is overwritten so frequently. So the stack allows us with a push to set aside a value in a register and then do a calculation in it, and then a pop at the end will restore that register's value to whatever it was before we started. So it's a really nice way, push and pop, to make your procedures not break other parts of your program, to preserve data, in other words. Okay, so that's my build-up. Let's look at the lab. What am I doing? Oh yeah, I want to bring back Firefox for a sec and go grab the lab code. lab 8. So a new one. All right, so all I've done here is I'm checking my folder too. I copied the lab code into a file so I can sort of do a little bit of a walkthrough. Now the notes in the lab technically should probably steer you in the right direction, but let's just go double check ourselves. Okay, so number 1, it's going to look familiar. You've done a get number. So that one is just, hopefully that's building up your confidence a little bit is the whole point of this. You know, not giving you the code, but having you go fetch it. Pay attention, this one's an uns 8, so the get's going to be U8. So this register is going to return a value in AL. So for get number, do we want to push and pop anything? Correct. So good one, Glazer. No. Get number is not a push pop procedure. Good one, Tyler. Get number is not a push and pop procedure because we want it to alter the A register. We want to have the A register have new data in it when the procedure is done. So not a push and pop. What about go again? Do we want it to change a register? Or do we not want it to change a register? So in other words, is go again a push pop or not? So correct again. Go again is not a push pop procedure. Great. And the reason it's not a push pop is because we don't want to preserve data in this case. We want to alter A so that when the procedure is done, the A register has new information in it. That's what we want. Show graph looks scary. And also, I'll sort of show you the hints. So it's long-ish. Oh, I already did it. That's a bummer. I took it away from you in this case. Okay, so but let's talk a little bit about why didn't I use the stack. So if you read the documentation for show graph, it doesn't say anything about returning data in a register. So when the program uses this procedure, it expects that no registers will be altered by it. Now, it is going to alter registers. I can show you where I've already done that. In my for loop, I'm overwriting the C register, but I don't want that to affect the rest of the program. So in this case, I do want to push the C register. And I've given you some hints here, but in this case, I do want to push the C register. Because I'm overwriting it inside the procedure, but I don't want to change it for other parts of the program. So I'll use the stack to preserve it and restore it. The A register is here because we're doing 8-bit division, and that means we need to make sure that any alterations to A that we do while we do the division don't affect the rest of the program. So I push A and C. That'll be familiar to you now. And then I pop C and A. So that's on purpose, remember. You pop in the reverse order of the way that you pushed. So let's see if maybe I should help you get started on total and average. Where are we on time? I don't want to ruin everyone's fun, but I assume that your bigger sort of fun is getting it to work correctly. That's probably the most satisfying thing. So let's at least start this one a little bit. So there's a reminder here. To compute the total and the average of these things, I'm likely to have to use the stack to preserve some data. But let's compute and display the sum of the 4 parameters and then make a decision about that. So I know I'm going to have to come back to 6 because I'm going to probably have to push something. Okay, so this procedure is not supposed to return data, it's just supposed to do calculations and print the results out. Compute and display the sum. So I'm gonna, they're 8-bit numbers. There's a good chance in this case that overflow can happen, so that's up to you if you want to deal with that. It doesn't ask you to, but if you add four 8-bit numbers together, there's a very good chance that they're going to be too big, unless you are clever about limiting the inputs to like 50 or something. Okay, anyway, so I'm going to zero out the A register, and then I'm going to start adding stuff. In fact, let's just put the first number in there, and then start adding. So I'll put the first number in there, and then I'll add the second number to it, and then I'll add the third number to it, and then I'll add the fourth number to it. So it's no requirement that you detect overflow, but it's not bad practice to detect overflow, because on the second project you will be required to code for that. So you might think about doing it on this lab just to be practiced at it, but I have not, so heads up. Which is a potential problem, right? This may be a bad result. But anyway, let's go ahead and do the whole thing. So compute and display the average. The average is the sum, which I would have put in AL, but it's already there. Isn't that handy? So I need to zero extend into AH, and then I will divide AX by 4. Hopefully everyone understood that. There's the sum of four numbers in AL. So AL already has the numerator in it. Then I zero extend AH. Then I do the division, and then I can say I like the way I did it above. You just have to remember that these are integers, so the average is not something point something. It's truncated down to an integer. That's the end of the job, right? I think that's the end of the job. Right, 8 bits, yeah. So that's just a note that the result is truncated. Remember, AH will have any remainder if you want to show that. So then the question is, what register has to be pushed and popped to preserve it here? So I have to sort of inspect my own code and ask myself, what register or registers did I alter with my code, so that I know what to push and pop? So what's the answer? Good one, Captain Price. So just EAX in this case is the only one. So whatever EAX was before my procedure started running will be restored for when my procedure is done. You might think of it as good neighbor programming, by the way, because if someone asks you to do some work for them and you like destroy their original data, they wouldn't be happy with it. Okay, so I will leave min and max to you. There's four numbers here, so you'll have to decide how you want to handle that, but right? And if n1 is less than n2 and it's less than n3 and it's less than n4, then it's the smallest number. You might consider using less than or equal to here, just in case there's duplicate values entered. And there is a note in here to remind you that this is probably one where you're going to have to push and pop to preserve register values properly. And then max will be very, very similar. And there's a reminder here to use push and pop to preserve and restore values as needed. There's nothing to do in main. I'll just kind of show you what I've done. And then I may have a reminder to give you, but let's look at main real quick. It's already all done. But I wanted to show you that I'm actually purposely, in this case, I want AL to be the first input, followed by BL, followed by CL, followed by DL. I want those to be in literally that order on purpose. If you think back to an earlier lab, by the way, I had you do DL as the first input, and CL as the second input, and BL as the third input, and AL as the last input. The reason why I had you do that is because I hadn't talked about the stack at that point in the semester, and you would have struggled to preserve the first input in A if we didn't do them in backwards order. So now that we know how to preserve the data, we can do things in forwards order if we want to. So notice what I do here. I get a number, and I want AL to be the first input. So what I do here is I push it on the stack right here. And then I get my remaining inputs and put them in B, C, and D in that order. But remember, every time I get number, A gets overwritten. So I sort of had to do a local push and pop. I push my first input, then I get the remaining inputs, and then this pop restores the original input back to A where it started. So when I get down to the rest of this loop, everybody is in the proper order. A is the first, B is the second, C is the third, and D is the fourth. So I actually used, in the main part of my program, a little localized push and pop to make sure that my first input is in A when I get to the main part of the program, the actual calculations part. Anyway, I hope that makes some kind of sense. This go again, by the way, it destroys the A, but at that point, I'm at the end of the loop anyway, so it doesn't matter because the next time the loop repeats, I'm just going to get new sets of numbers anyway. Okay, so hopefully that's enough for you to knock this thing out. These min and max are just pain in the rear if-else if type statements. There's no fancy trick here. You just have to do a big long bit of logic. If n is less than or equal to 2, and n is less than or equal to 3, and n is less than or equal to 4, then n1 is the minimum number. And you'll have to repeat that. So you can probably do some copy and pasting, but it's expected you're going to have to do some brute force logic in there. So Captain Price asked, do I have to make sure that they're not all the same value? What you should do is make sure that that doesn't break. So it should be true that if they're all the same value, that the minimum value is that value. So your logic should work for that situation. And the hint is kind of testing for less than or equals to, as opposed to just less than. It will pick off things like that faster. Which is my last note is there's just like 2 or 3 people who occasionally don't, it appears that you don't run the program and actually observe its outputs to see if your code's right. So remember that's a pretty important last step before you submit, is to compile your program, run your program, feed it inputs, and make sure that it's actually doing the correct calculations. Yeah, so Captain Price has done the calculation. If you want to guarantee no overflows, then make these be, so one thing you could do is make them all, well, that's 63, right? If you make all of these 63, then you won't get overflow for the sum, or something less than 63, right? So you could say like 0 to 50 if you wanted, and that way you're guaranteed to prevent overflow. You are allowed to do that, to alter these so that overflow can't happen. Or you can allow overflow to happen and just ignore it. Or you can allow overflow to happen and detect it and print an error message. Totally up to you. The the main things we're looking for is to practice using the stack to preserve and restore data, particularly for our procedures. And the value of that for learning purposes is so that you are aware of the stack. You know how stacks work. They're very useful in broader computer science. And then you've had a chance to practice using push-pop instructions to do that work. You can. So there's a question about, I'll go ahead and do that. So this will be bonus content for the last 5 minutes to answer Captain Price's. So that's everything that probably you need, but let's do Captain Price's idea, which is, could I somehow detect overflow and then like promote all the values to 16 bits? And you can. So let's do that. Now there's a trick here, because overflow could happen anywhere. It could happen anywhere. So let's write a procedure for that, because that would be, no, let's not do that. Let's just detect it right here. So after any one of these adds, overflow can happen. So here's the way to do Captain Price's idea. If you detect 8-bit overflow, you can promote everybody to 16 bits, and here's how I would do it. So if I'm getting overflow, well, the first thing I'm going to do is I need to promote 4 to 16 bits. So the thing to do as a starter is to make sure that you zeroed out all of the 16-bit registers where you're going to perform your promotions. And then you can move if you move these 8-bit into their 8-bit partners, the H parts are all zeros, so you don't actually affect the value, you just affect the size. Then you can do the adds. So it's totally doable, Captain Price. If you're still here, let's finish this thought so that we don't do it wrong. So it's a lot of extra work, but it's very doable, and you would have to repeat it basically after every add. So the trick about the carry is that you have to check for and detect it immediately after every add that could lead to it. So I have to check it after the first add, and then the second add. Now I could write a procedure to embed all this stuff. I'm just not going to do it. And after the third add. Yeah, and typically you would have done this promotion at a different place in your program to avoid this problem. But it's totally doable to promote your values up using registers. This does change. So to finish the thought and close the class down for the day, this changes my push-pop problem. So what has to be pushed and popped now? Let's start with the pushes. There we go. So because I'm using all those registers now for my little math promotions, I got to push them all. Changes the pops. That's the tricky bit. So what changes about the pops? In the reverse order. So I did D last. And the reason why they're in reverse order, of course, is because that's the way the stack structure works. So DCBA should mirror ABCD. So that's what I would have to do to perform that little trick of promotion. But that was a good question to ask because I got to do the extra pushes and pops. So all that stuff that I just did is not a requirement. If you read the lab, it just says compute the total, the sum, and the average. And it does not say anything about handling overflow. So if you want to handle overflow, you can. You can detect it and present an error message. You can detect it and promote all the values to 16 bits like I've done here. Or you can, if you want, prevent the overflow from happening in the first place by not letting your user type numbers when added together would overflow. So that's a legitimate way to handle it as well, and it's totally up to you. I would probably arbitrarily make these like 50 because the point is really to demonstrate an algorithm anyway, but that's up to you. Okay, I think I'm done. I'll wait for a second or two with questions, but otherwise I hope you have a great week ahead. Just let me know if you encounter any problems. Please consider using Piazza to swap out questions and answers if you should have any. But otherwise, we'll take a breather for a week or two on the project stuff, but when there's an opportunity, then I'll call your attention to a moment that might be a good time to start the second project, but that's many weeks in the future right now, so I think we just go with the normal routine this week. So take care, and I'll see you next Monday, I hope.